we have Ojas Ramwala, and he's a PhD candidate for University of Washington. He's going to present explainable AI for biomedical image processing.
Awesome. Thank you so much. First of all, it is a very surreal moment for me to be here. The first time I was at PyData was 2 years back when I was a first-year PhD student at the University of Washington as an attendee. So I'm immensely grateful to the organization team that today I'm here back as a speaker, as a final-year PhD candidate at the University of Washington, Seattle, where I study how to advance the clinical translation of AI algorithms for medical imaging applications, specifically for mammography-based breast cancer screening applications. Also, I know that I'm standing between you all and lunch, so I'll try to keep my talk as appetizing and digestible as possible. Thanks. So, first of all, I'd like to start with what are the applications of AI in biomedical image processing. So as an undergrad, I was immensely interested in the field of image processing, specifically biomedical image processing. And that I'd like to sort of, try to work with curious students in my cohort to essentially build applications, for example, in ophthalmology, like, trying to build a deep learning model that could perform the delineation of blood vessels from a retinal fundus image. So like an application on retinal vessel segmentation. Or we would like to build an application in radiology. Essentially, we would build a deep learning model that would process a chest X-ray and detect whether a pneumonia is present or not, and then potentially think whether it has applications for COVID-19 diagnosis or not. Or we could think about applications in throat image analysis. For example, whether a particular throat image has tonsillitis or not. Or we could think about applications in pathology image analysis, like spatial transcriptomics, trying to link histopathological images with single-cell RNA sequencing datasets. Now, I feel grateful that I've got a chance to sort of collaborate on such interesting projects, contribute to some of the interesting ideas in deep learning. But this was a few years back, before I even started my PhD. And you don't really see these algorithms in clinical settings, do you? You don't. Also, if you were just a bunch of undergrads, but then there are proper teams who build robust, generalizable deep learning algorithms. In fact, I was just checking this morning that there are over 1,000 FDA-approved AI algorithms, which can be used in clinical settings, but not really. So, the main question that I've been asking is how do we improve the clinical adoption of AI algorithms for biomedical image processing? To essentially understand what's the missing piece of this puzzle. So, we start by developing all these, interesting models. But what is missing? Is it the generalizability of these deep learning models? Do these have some sort of latent biases present within them? Do they underperform for some specific patient subpopulations that can potentially limit their integration into real-world clinical settings? And to that end, we developed a framework called as Explainable AI, which essentially equips health institutions to establish cyber infrastructures that they can use to perform external validation of deep learning models and customize it for, let's say, medical imaging applications. So this can potentially help with the concern of generalizability of these deep learning models. But let's say we now have a well-developed, sophisticated model, a great neural network that is generalizable, that is not biased, that performs really well, and has the potential to be integrated in a real-world clinical setting. So we would have an amazing black box. Essentially, clinicians would now have a powerful model, but they would not really know what went behind its inference mechanism. How did it make certain predictions? So, for a standard biomedical image processing application, we can have all sorts of medical imaging data. Like, we can have these mammograms for breast cancer screening, chest X-rays, histopathology images, retinal images. And our doctors may want to harness AI for biomedical imaging to essentially further biological discoveries and potentially inform clinical care. So they'll think about how we can integrate an AI model into our workflows, which could make some predictions and then leave them perplexed as to why did it make a certain decision. So this AI model may try to, let's say, detect diseases and then could help clinicians develop more patient-specific personalized treatment options, more strategies and personalized interventions that can help them in their clinical workflows. So how do we unbox this black box? We have this big conundrum with the accuracy versus interpretability of these deep learning models, where these sophisticatedly built complex models may not have a very interpretable reasoning mechanism for us to digest. So why would we really want to unbox this black box? Essentially, why would you skip this amazing sunny day in Seattle and listen me talk? Is it really that important? Well, the goal of explainable AI is to intuitively explain the predictions of machine learning algorithms while adhering to the needs of various stakeholders. Now, that's a pretty packed statement. But with this talk, I'm not trying to say that here's the best explainability method and adopt it and that solves all problems. What I'm trying to say here is that let us explore some of these techniques together, spark some interesting questions, and see where these conversations take us. But what really constitutes a good explanation? How do we understand whether an explainability method is even useful, even helpful or not? For example, in medical image processing applications, we would want to be able to generate scientific hypotheses based on AI models and the explanations that we can generate from their predictions, from their reasoning. We would want to drive clinical knowledge discovery. Moreover, it would be good if we can diagnose model failures, if we can understand the trustworthiness of these deep learning models. We would want to audit for all sorts of unwanted dependencies or any shortcuts that the deep learning model may be taking to come up with seemingly accurate predictions. We would want to enable regulations. We would want to, at the end, build user and organizational trust, but also help AI vendors, the ones who build these robust deep learning models, to understand their models better and potentially do more fine-tuning efforts, more targeted improvements to their deep learning models that they can then be integrated into our clinical workflows. For example, I'm really passionate about the field of breast cancer screening. So let us say that we have this amazing black box model, a deep learning algorithm that looks at a mammogram and says that cancer is present. But how do I, or how does any radiologist understand that why did the model say there is a cancer present? How would they even begin trusting its predictions? For example, a clinician may go about reading the entire mammogram and potentially delineating where the tumor is present. Essentially, their qualitative interpretation will be more meaningful when they are able to locate the exact position of the tumor and say that cancer is present on this mammogram. So, do we feel that such bounding boxes, such segmentations could be really helpful? Let us say we have a deep learning model or an explainability technique which is wrapped on top of it that essentially helps us understand where exactly the model was looking while making these predictions. And of course, this is not specific to the field of breast cancer or mammograms. This is across diseases. This is across imaging modalities. So do we feel such segmentations could be helpful to assess the imaging features that could be driving the inferences, the results of that deep learning model? Do we feel that? Yep, that's good. We agree. So let us try and better understand that what is the real challenge in coming up with such clear notions of where the model was exactly looking at. Especially in the field of medical imaging, these are essentially high-dimensional data sets. They have like a large feature space in that each and every pixel could be a feature. So as these images grow, the feature space expands and interpretability gets more and more complex. So how do we make these predictions clinically interpretable and help our clinicians, our radiologists, our pathologists to be not perplexed? And here comes techniques like post hoc explainability methods. Essentially, there has been significant research in coming up with these visualizations known as saliency maps that are aimed to explain individual predictions of medical imaging algorithms. These are algorithms that are designed to highlight imaging features which are deemed relevant by the deep learning model. And the ability to infer the salient regions of medical images that are crucial for models' predictions can help interpret the underlying inference mechanism, the decision-making process of these robust, generalizable, but black box deep learning models. So, how do these really work? Essentially, like in our case, we would have a mammogram. We would have an AI algorithm that made a prediction on cancer or not, just a simple binary prediction. And then there will be a saliency method that wraps on top of it, which ingests the medical imaging data and the algorithm, its predictions, to come up with a visualization that helps us understand the relative distribution of feature importance across this entire image through somewhat like a heat map or a saliency map. Essentially, we would like to understand whether the saliency map can in some sense help us interpret the decision-making process or even gauge whether the model is even looking at the right place while making its predictions. For example, consider this case, wherein which we would have a ground truth bounding box and also the saliency map which is generated by this explainability technique. And then we can go ahead and confirm whether there is an intersection among the predictions of the model or its interpretations and the ground truth findings. And after that, could we potentially say that the model makes sense? And this is not only constant for just mammograms or grayscale images, like it is across modalities. For example, whole slide images in histopathology, or MRI scans, microscopy images, CT scans. You can do such similar analysis for almost all models, all modalities. Now, the real question is, can we link these saliency maps, these heat maps, to clinically meaningful findings? Could we harness AI applications for medical image processing and henceforth drive more clinical knowledge discovery? So first, let us see this particular case, wherein which we would have some input imaging data and some saliency map which would be generated. And then we can go ahead and ask whether it is detecting the lesions well, whether it is identifying the type of lesion. For example, in the case of breast cancer screening, it would be very important to know whether the model's predictions corresponded to the detection of masses or calcifications, such that the radiologist can now think of the next steps, like do they need a focused diagnostic image? Do they need shorter screening intervals? What are the next steps that a radiologist can take to help the patient? Or in the case of chest X-rays, we see that we can go ahead and validate whether the model is picking up on clinically meaningful attributes. Essentially, through these notes, we can see whether, is it answering more intricate, more detailed questions well. We can go ahead and dive deeper into the model's predictions and understand what exactly is going behind its predictions. And this is not just for, as I said, grayscale images like mammograms or chest x-rays, but you can do it for like more for multi-scale images, like for microscope images, for whole slide images, wherein which you can see whether it is looking at the cell type correctly, whether it is picking up on the right set of morphological features or not, and go ahead and make more hypotheses about its inference mechanism, go ahead and validate, understand its decision-making process. So is this it? Is our problem solved? Because all of these are from like top journals, and companies have in fact spun up out of these amazing deep learning models. Like they would come up with their amazing model, they would provide more details into their architecture, they would do an amazing job explaining it, they would show these saliency maps to essentially confirm that not only is our model making the right predictions, but is also looking at the right places. Bazinga, that's it, that's all we need, right? So, are saliency maps always useful? Is this the solution to all questions on explainable AI? How about this? Do we think the saliency map is useful in this particular scenario? How many of us think that this saliency map is really helpful in understanding the model's predictions? I see one hand. It's tricky to interpret this saliency map because it highlights a sizable proportion of the image. It is not very clear as to where exactly is it looking at. What is the most meaningful clinical attribute that it may be picking up on? How about this? Do we think this is interpretable? Can this help clinicians? A saliency map like this? How many of us feel that? Not even one hand. Why? We just established that saliency maps are beautiful. Like, they are the most amazing thing that deep learning researchers could have created. And now there are no hands to understand. Why? It looks like it is highlighting all over the place. Like, is every region important? What is the most meaningful clinical attribute that can be extracted from this image? It's not really clear. How about this? In this case, in this last image, this visualization, do we think saliency maps are helpful? Is this visualization helping us understand the model's latent inference mechanism, the magic that the model is doing? To me, it's even unclear as to what exactly is it highlighting. So now we would want to test the saliency maps better to understand whether they really hold potential to explain deep learning models or not. So the first question that we should ask is that are saliency maps even sensitive to parameter randomization? And by that, what I mean is that let us say that we have a deep learning model. So if you see this second column called trained, it is like an amazing deep learning model, which has like, good AUC, it has good performance. And now the saliency map is essentially highlighting that, these two bounding boxes, these two regions were incredibly important to the model's decision-making process. And now let us just consider the same model architecture, but an untrained model that has no knowledge of the task, has no knowledge of the data set. It is just a random algorithm that will give predictions like a flip of a coin of like cancer or not, anything. So now this is a random model. And in this case, we see that the random model is like picking up on random imaging features on the image. So it appears that this trained model does an amazing job compared to flip of a coin. Like not only it has amazing AUCs, but it also has an interpretable and a clinically meaningful inference mechanism. Great, I'll go ahead and make a company out of this model. But wait, how about this? In this scenario, a very well-trained and expensively trained deep learning model, its sophisticated deep neural network architecture, picks up on the same features as a random model an untrained model. Like they're essentially looking at the same thing while making predictions. So does it imply that millions of dollars that are potentially spent to build this deep learning model, this state-of-the-art model, is as good as a random model? Is it just picking up on the same set of features? Or is it a limitation of the saliency method in helping us identify the true regions where the model is looking at? The next question that we can ask is, are saliency maps reproducible? Essentially, columns 2 and 3 are different deep learning models, but they have comparable AUCs. They are like doing decent performance. They have almost the same performance. And then we see that they are picking up on the same set of features. So how do we feel about this example? Does this mean that the two models that are sort of giving comparable performance are now looking at the exact same clinically meaningful attributes? Thus forth, implying that both of these companies did an amazing job creating a model, and then maybe a clinician just has to see which one is cheaper and integrate that. But how about this scenario? The same two models now looking at different places in the model. Like, do they have a different inference mechanism? Are they learned in a different way? Or is this a limitation of the saliency method in helping us understand what are the most clinically meaningful features that the algorithm might be picking up on? We don't know if these saliency techniques are even reproducible or not. Final question, are these saliency methods repeatable? Essentially, I take the same model architecture, exact same construction. I train it today. I call it model A. Now, I train it tomorrow. Exact same data set, exact same learning paradigm, everything as is, and call it algorithm B. Ideally, it's the same model. It has learned the same thing, and it is giving the same performance. Now, a saliency map, a saliency method, should show that they would now pick up on the same set of features, because in some sense, they are same model. And we see that maybe in this case they do. So the sanity check has passed. The models are doing well. They are learning the right set of features. But how about this? The same two models now pick up on different things on a different scenario. So unfortunately, most of these saliency methods work well in ideal scenarios, the ones that we do not usually see in clinical settings. You can potentially use these saliency maps to fool a clinician, to fool a radiologist, to fool the authorizations that our model is not only doing an amazing job, but it is also interpretable. It is like training to become a radiologist. And then you see that there are these cases where it just does not work really well. Another mind-boggling feature is that this is not just consistent in medical images, but a recent study in natural images found that like a plethora of these well-built saliency maps, they just work as good as edge detectors. Like their results, their visualizations are like simple edge detectors that are agnostic of the data, that are agnostic of the deep learning model. So now, it is not really clear as to whether these saliency maps are clinically meaningful or not. Now that's a puzzle. We do not really know the solution to this. Or maybe we do. There has been some interesting research along those lines. And one such solution that I'd like to talk about today, which I'm not saying is the ideal or the perfect solution, but an active area of research, which is counterfactual explanations. Now, what does it really mean? Let's try to exemplify that. Let us say that we have a medical image classifier, a simple binary classifier, which is just sort of taking in images and then putting it into two bags, class A and class B. For example, in the case of mammograms, it will say that class A is, let's say, potentially healthy. Class B is like abnormal with, let's say, cancer. It has a disease. For those curious, there's a cancer present here. Like this is the tumor region in these mammograms. Now, similarly, it could potentially try to classify these pictures of skin, like whether they are malignant or not. So class B is the one with a lesion, for example. Or in the case of chest X-rays, like class B is the one with a disease, and class A does not have a disease. So how would we go about sort of understanding the interpretation of this medical image classifier? And I'm not saying this is like a generalist model. This is just for our explanation. And of course, the decision boundaries also don't really look like these are like probability functions. But yeah. So the question that we ask with counterfactual explanations is, how should the image be altered to flip its predictions? Essentially, can I change some features about this image in a way that the model now classifies it rather than class A to class B? Or alternatively, here, it classifies this mammogram with cancer as being without cancer. Could we do some more realistic, clinically meaningful changes to these images and then try and understand whether it alters the predictions of the AI model or not? But the most important criteria is that these images, these changes, should still be realistic. It should still resemble the reference image that we are considering. Now, let us consider this example of a dermatology AI classifier. And we have this reference image here. And you try to alter some features of this image that could change its predictions either to, let's say, class A or change its predictions to class B. But we want to make these changes be clinically meaningful. So we had this amazing work that came out from our university, and I'd like to talk about it. This is not my paper, but yeah. So essentially, they came up with a deep learning model, a generative model, which essentially generates these realistic counterfactual images. Essentially, we have a reference image, and then it would generate counterfactuals, some changes in these images, and then give the reference image and the altered images to the clinician to understand what would have changed in these images that led the classifier to predict a different outcome. And they can do this over different images with multiple experts, with multiple clinicians, and try to interpret that what clinically meaningful attributes changed in the images that caused the model to now change its decision of whether cancer is present or not, for example. And this was very interesting because now the clinicians were able to identify features that the model may have picked up on while classifying whether an image had cancer or not, for example. Like here, we see that if a lesion is present, they identified that the model was seeing whether the pigmentations were dark or not, or sort of, what sort of pigment networks were present, or what were some of the structural features that were present when a model identified a particular image as having cancer or not. Of course, I'm not a dermatologist, but what I'm trying to say here is that you could have a generative AI model that could be conditioned on the inference mechanism of the deep learning model we are trying to explain, which then generates realistic changes to the images, which can be inferred, which can be interpreted to understand what changes in the model drove its predictions to class A or class B. This is an alternative solution, but this is not to say that this is the ideal solution. There have been challenges with trying to operationalize this, especially with the effect that it is not usually very easy to make changes into the model which could be directly clinically interpretable. Or sometimes these changes may actually change the distribution of the images themselves. So these are some of the open challenges which are still to be addressed in terms of developing techniques that can more faithfully explain the model's inference mechanism. But nonetheless, the research in counterfactual explanations has been very, very interesting. So we sort of saw a whirlwind of techniques to essentially see what type of mechanisms or visualizations we maybe use to sort of, explain the latent decision-making process of these amazing deep learning models. Like we could have somewhat of a segmentation. We could have these saliency maps that can try to pinpoint where the model was looking at, or we can have these counterfactuals that can essentially help us understand what changes in the model drove a change in model's predictions. So towards the end, I'd like to very quickly talk about the clinical utility of each of these methods. For example, these saliency maps. What may be the clinical utility of a visualization like this? Would anyone love to take a guess? What if a clinician just wants to know the approximate location of diagnosis so that they can do more follow-up, more diagnostic imaging, maybe think about screening intervals, for example. So this is where saliency maps can still be useful from a more user-centered perspective. How about these segmentation maps? How could these be more or less helpful than saliency maps? What if we want a precise location of diagnosis? This is when the segmentations would be incredibly helpful. And for the last one, how about these counterfactual explanations? Where would these be immensely helpful? This is an interesting question. Any thoughts? Yeah? Oh, training the models themselves? The clinicians. Oh, yeah, that's actually an amazing answer. Like you could use these counterfactuals to essentially train them that, what changes in the model corresponded to like whether an image was benign or malignant. And another interesting use case would be to understand the progression of the disease, like from mild to moderate to severe. So essentially, yes, again, to train the clinicians, for example. So these are some of the ideas that I found interesting in the field of explainable AI. These are not my ideas, but just some very interesting concepts that can be leveraged to advance the clinical integration of deep learning models into real-world clinical settings. And with that, I'd like to be open for questions, conversations. Thank you.
Yeah, thank you. I was wondering if you could speak a little bit about how the saliency maps are generated. I think on one of the slides you had them as two separate boxes, but I'm imagining this, the model that generates the saliency map probably has access to layers to the diagnosis model.
Yeah, so I think these saliency maps are essentially, let us take a for example. So these are like multiple saliency methods. And in a nutshell, how do they work is that they wrap on top of these deep learning models. And they could be based on the backpropagation mechanism of these deep neural networks, essentially how the gradients pass from one layer to another. How do the feature maps change from one layer to another? So they have been built very sophisticatedly to understand at a more pixel level to more feature level as to what changes in the model. So that is not to say that they are not intelligently built. They just have their own failure modes.
But they have tendrils into the layers.
Yes. They are actually based on the deep learning model themselves. Yeah.
Cool.
Thank you. Very interesting talk.
Thank you.
So we saw some failure most of the saliency maps, right? Whether they were showing like two big areas, whether they had jitter, like from one training to the other, all of these things. How do you think about the distinction between the methodology being the problem versus the accuracy of the model?
Exactly.
I could imagine, like, if you had tenfold data, right? Could this model just get good enough so that this doesn't happen? What's your thoughts on that?
Yeah, I think that's a very interesting question. Like, how do we pinpoint whether, the visualizations that were generated by a saliency method, were they due to the lack of just good learning of the deep learning model? Was it just a bad model? Versus was the visualization bad? Was the saliency method bad? So that's like this conundrum that we have as to, there's this lack of understanding wherein which we could pinpoint whether the model had bad feature representations, or was the saliency method just not good enough in representing the true underlying decision-making process? And I think that's actually part of the question. Like, we don't really understand these challenges, in terms of just pinpointing or identifying whether the model had bad representations or good decision-making process or not. But yes, to your point, we can potentially think more about the generalizability of the method or like the model itself. Like, does it perform well across diverse subpopulations? And was this just an off case where the saliency method generated a bad visualization that was not faithful to its predictions? It is still possible that the model was looking at the right place, but the method just failed to appreciate that. So yes, that's a tricky question, and that is why the research has moved away from a lot of these gradient-based traditional saliency maps to come up with more, more detailed methods that could be faithful to the model's deep learning or the model's deep representation space.
When you introduced the part where you talked about generative AI being being used to generate counterfactual explanations. How would you constrain the legal moves that the Gen AI does? Because in current systems, Gen AI kind of struggles at making modifications, like making the glass full.
Yeah. I think that's a very interesting question. Like, how do we condition the model to come up with images, come up with counterfactual images that are realistic, but still change clinically meaningful attributes? So there's this technique called, just a very popular technique called generative adversarial networks, or GANs. But then they could be trained with something known as explanation by progressive exaggeration. So what this means is that you make very minor changes to the images that are generated by the deep learning model, and you closely observe how far does it take, sort of away from its decision-making boundary. This is a gross undersimplification of its process, but for folks interested, they should really check out this paper called Explanation by Progressive Exaggeration. It is based on generative adversarial networks, but of course we have these new models coming up based on diffusion models. So I think last year or so, another paper came out which is called diffusion visual counterfactual explanations, wherein which they have this clever technique of taking cone projections to essentially condition the model's image generation process, such that it is not just making any futile images that may not be relevant, that may not be clinically meaningful. So there are conditioning mechanisms in place, but as I was saying earlier, operationalizing them is really challenging. But this is definitely an interesting research space.
Thank you. Just kind of as a follow-up to that question, this idea of generating counterfactuals, I assume that the subject matter experts have to then look at these and decide when they would choose if it would be cancer or not. Mm-hmm. So you're limited on that. But it also occurs to me that that also might prevent the model from ever being more correct than the subject matter expert. Some of the promise of this, people hope that an AI might be able to tell even better, maybe by looking at unexpected places. But does explainability kind of put an implicit cap on that?
Yeah. I think that's a great philosophical question. Like, do these regulations, do these checks that we want to put on these deep learning models, can they impede the development of interesting, robust, generalizable deep learning models that can potentially drive knowledge discovery, not only in the clinical space, but for various other domains? And an important aspect to consider is that how do we differentiate knowledge discovery as something that is actually clinically meaningful versus just some imaging features that may be mimicking, for example, a lesion that could fool the model to make certain predictions. And this, sort of comes to more interesting questions. Let's say in cancer applications, we'd want to think about oncogenesis. Like, does this make interpretable changes in the genetics of a person, for example? So then you'd have to enter the space of multimodality. Like, we would not only focus on images, but then go about thinking, how do we integrate clinical factor data or genetics data and see if changes in the images, do they also, or changes in a condition that is reflected on an image, is it also reflected in the genetics of a person or not? And these are all important questions for which we'd have to work in an interdisciplinary fashion with clinicians, with radiologists, with our actual stakeholders, like going beyond the technical aspects of deep learning models and working more in a collaborative fashion to understand what is lesion mimicking versus what is actually advancing our knowledge. So, yeah.
Thank you. Great talk, Ojas. So I was curious from the beginning if other forms of metrics, like say Shapley values, are used as a comparator to saliency maps, mostly because the saliency maps seem like you need to have a human eye to review those, and they're not that interpretable. So there's lacking some form of context, which if you were to use segmentation, right, would that have informed additional features like segment of the lung or breast? But if you were to go down that road, would you even use saliency maps versus something else like Shapley values?
Yeah, I think that's an interesting perspective. So SHAP is also like another feature importance or a feature attribution technique, which has been very widely used, let's say for more like, let's say, where we have discrete features. And SHAP has also shown, I think, promising results for image explainability and potentially for medical images as well. But then again, when it comes to understanding the model, we cannot totally circumvent the requirement of having a subject matter expert. It would still need a human eye or human expertise to essentially confirm where the model is looking at. Like if we try to come up with a visualization that helps us understand the relative distribution of feature importance across an image through either a saliency map, through either counterfactual explanations, through a SHAP-based technique, we would still need a subject matter expert, fortunately or unfortunately, to help us understand whether those predictions make sense, whether those interpretations make sense, and whether the inference mechanism of that deep learning model can be linked to clinically meaningful attributes or not. So yeah, we don't want to go away, or we don't want to sort of remove the radiologists from the loop or the clinicians from the loop. We definitely want humans in the loop when we try to explain deep learning models. Now more so than ever. Yeah.
I was wondering if you could speak about, speaking of the loop, it seems like there's a lot of I don't know what you could, edge data that you could be getting from, the use in practice. So at the point of application of, say, one of these models, it gives a yes or a no, or it segments or whatever, right? Later on, in that clinical setting, I would imagine there's going to be, it's not just what the maybe a radiologist is like, this is BS, it's wrong. So I could see you could feed that in, but even better is maybe the progression of what happens later when they find out what it really was. Can you is sort of the system set up to have a closed loop like that? Or does that data kind of just get lost right now? And do you see progress happening in that direction?
Yeah. So I think we can always have these challenging corner cases or edge effects, as you said, where like a deep learning model, a robust generalizable model would do relatively good for the most part, but then it would just underperform in certain scenarios. So the question is more like, do we have mechanisms to essentially understand what were those edge cases that the model underperformed on, and what role might explainable AI play in such scenarios, right? So I guess one of the most important aspects of explainability is not just to defend or advocate for our deep learning models to clinicians or advocates or to radiologists, but to also help our own targeted fine-tuning efforts. For example, if a company would know that their model is underperforming on such and such edge cases, they would like to have better mechanisms to understand the reasoning behind those specific predictions, or in the field of explainable AI, we call it local explainability, so that we can understand where sort of the model went wrong, and like, do they just need to fine-tune the model on such edge cases, like just retrain the model, or like specific layers of the model for similar edge cases? Or is there something fundamentally missing in the deep learning model itself due to which it is going wrong? So yes, to your point, there are mechanisms or checks that usually companies that are trying to sort of put their models in real-world clinical settings do. And most of these models actually, or most of these AI vendors, they work in close collaborations with clinicians, with radiologists, with pathologists, to better understand like what are the failure modes of their model. Otherwise, they could be in big, big trouble. So yeah.
Okay. Thank you.
Awesome. Thank you so
Speaker.
much.
And